All right. What I want to do today is a few somewhat more advanced problems that will possibly help. This figure is of two circular coils with radius A, each wound with N turns of wire carrying current I and circulating in the same direction in both coils. And that same direction is kind of important. So if we imagine that the current is going in this direction in each coil, the magnetic fields of each of these things, you use a right-hand rule to figure it out, they're each going to be making a magnetic field to the right. And that's on either side of the things. And so we're going to be interested in the region in between here. These are called Helmholtz coils. And these are the coils that produce the magnetic field for that electron beam apparatus that we have in the classroom. And so we're going to be doing some work with this. And the first thing we'll do is derive an expression for the magnetic field B, the magnitude of the magnetic field, at a point on the axis, a distance x to the right of point P. Well, for this, I'm going to have to go to some other paper because I just can't do it well enough here, but I'll show you how we'll do it. First thing I'll do is, I guess I'll draw a line, a horizontal line, and that'll represent, oh, where's my black pen? That's what I'd rather use. There it is. We'll imagine that this is the point P that they have labeled in the diagram, and P is equidistant, or the midway between the two coils. And so there'll be one of the coils is here. We're looking at it just kind of from within the plane of the coil, and the other coil is going to be here. And we want to figure out the magnetic field at distance x to the right of point P here. And so if we call that point X, this could be the origin of our X coordinate system. And then the coils are separated by a distance equal to their radii. And so they have that, which makes this distance here A over 2. And this distance here, A over 2 as well. So now remember, both coils are producing a magnetic field that's going to be to the right, and I'll just sketch that in here like that. All right, well, something we're going to need is the expression for the magnetic field on the axis of a coil. And this is developed in the book, and I talked about it, I think on Monday, did an example problem with that. But it'll be this. For a single coil of N turns, or like just this one or just this one, it would look like mu naught N I A squared divided by, pretty complicated expression, 2 times x squared plus a squared to the 3/2. Now, this x is not related to this x here. It might be better to call this thing d, maybe, d squared. It's an x in the book, but d would be the distance you are along the axis away from the center of the coil. And so we'll be able to use this expression here. And in fact, in our case, one of the distances away, the distance you are away from the left coil here, is going to be A over 2 plus x. And the distance you are away from the right coil will be A over 2 minus x. So A over 2 minus x is the distance here. And then A over 2 plus X is this distance. And so we'll have an expression with that in here for D and an expression with that in here for D, and we'll be adding those two expressions together. So in this case, the magnetic field is going to look like this. B equals mu naught NIA squared on top of both expressions, actually. And again, A is the radius of the coil. That's why that shows up here. And then for the left coil, the contribution will be A over 2 plus X quantity squared plus A squared. And that's to the 3/2. And the contribution from the right coil will look very much like that, except it's going to be A over 2 minus X here. So mu naught N I A squared over 2 times A over 2 minus X quantity squared plus A squared and to the 3/2. So that's actually part A of this problem, wherever I put it. Derive the expression for the magnitude B of the magnetic field at a point on the axis A, a distance X to the right of T, which is midway between the coils. So we have that expression. And it's a scary looking expression, but if you were actually solving this problem, presumably you'd know the number of turns N in the coil and the distance between the coils, which is capital or A here, which is also the radius of either of the coils. And so you wouldn't have quite so many unknowns here. For the coils that are in the classroom, the first time I set them up, I was able to develop an expression like this for getting the magnetic field strength between them, which is something that you need for doing the experiment correctly. But something I didn't know, I could measure the distance between them to get the value of A, or the radius of them. Something I didn't know was how many turns were in the coil. And so I was kind of mystified as to how we might do that. So I thought I could work backwards from measuring the radius of curvature of an electron beam for a particular current and figure out the number of turns in the coil, except it's not so easy to get the radius of the electron beam. But then the next year, when I was doing the experiment, I noticed that written onto the electronics of the device is the strength of the magnetic field given a current of I. And so you don't have to know the number of turns, you just measure the current and multiply it by that constant they give you. So you could factor out the I here, and all that junk is going to be buried in there. But the next part of this problem is to graph B versus X for X equals 0 to X equals A over 2, and compare this graph to one for the magnetic field due to the right-hand coil alone. Well, that's not such an easy thing to do because you've got all kinds of stuff in here. However, I can simplify this expression a bit, and I'll show you how I'm going to do that to graph this expression. And I've actually already set this up in a spreadsheet, but B, I can factor, I've got common stuff. Mu naught NIA squared over 2 is common to both terms. So I'll just pull that out. And then what I'll have left inside parentheses is something that looks like this. I'll have A over 2 plus X quantity squared plus A squared, and that's to the 3/2. And then I've got this other term here, which is going to look like this. And I'm just trying to figure out a way to graph this thing right now. A over 2 minus X squared plus a squared to the 3/2. So here's what I'll be doing. Now, this stuff isn't going to add anything to the graph. It's just going to scale it up or down. And so I don't really need to worry about this stuff out here. And then what I'd like to see is how the magnitude of this stuff changes as I go from an x value of 0 to an x value of a over 2. I'm just going to pick a value for a and then let x go from whatever that, or go from 0 to half of that value. So what I did was I just let a equal 1. Okay. And then I can scale it, and I'll let x go from 0 to 1/2. And what that gives you is the magnetic field, a kind of strength for it, but it'll be proportional to the strength of it as you go from the very center of this thing all the way over to the center of this right-hand coil here. So that's what it'll give me a graph of. Well, when I do this, if I let a equal to 1, the terms in the brackets here simplify a fair amount. And inside the brackets, I'll have 1 over, let's see, I'd have, if a is 1, then the first part is 1/2 plus x, quantity squared, plus 1 squared, which is just 1, and that's to the 3/2. And then I'll also have a term over here, which is 1/2 minus x, quantity squared, plus 1 to the 3/2. And that's what's inside the brackets of this expression here. And then I actually blew up these terms here, and I would get 1 over, square this binomial, and you'll get this squared plus 2 times this times that, plus that squared. And I taught elementary algebra, which is now called intermediate algebra, at Big Vin for a long time. Anyway, you get basically 1/4 plus x squared. And then we've got the plus 1 that's left outside there, and that's all to the 3/2. And for the other term, I'll get 1/4 minus x plus x squared plus 1, and that's to the 3/2. And this is for the right-hand side, and this is for the left-hand coil. But if you simplify that a little bit farther, you get 1 over 1/4, I'm going to write as 0.25. You'll get x squared plus x plus 1.25 to the 3/2. And on the other one, you'll get 1 over x squared minus x plus 1.25 to the 3/2. Okay, so that's what I have to graph. And this isn't so bad anymore, although they're kind of scary. But I'm going to switch my view here over to, let's see, to the spreadsheet that I put this in. And get my cursor over there. Okay. Over here, I've got the left coil, a column for the left coil, and oh, let's see, you can't quite see all the way over to there. Here we are. Here's the values of x, and I have them go from 0 to 0.5. Remember, a is 1, and X is supposed to go from 0 to 1/2 of 1, so 0 to 0.25. And I just made step sizes of 0.02. And so it looks like that. And then if I double click on this, you can kind of see the formula. It's 1 divided by, in parentheses, x squared plus x plus 1.25 for the left-hand column, or left-hand coil. Better get out of there before I screw it up. And then for the right coil, it's very similar, except I've got x squared minus x plus 1.25, and then that's to the 3/2 power there. Whoops, I gotta be careful. Anyway, and I do that for all of those points, and then here I've got the two things added together, and so you can see what that looks like. All right, well, unfortunately, when I made the first graph, I made the dots too small, and I haven't been able to figure out a way to simplify that too much. But this is the curve for just the right-hand coil. And it's actually, I was a little surprised that it's a little bit stronger in the middle of the thing. And then it gets weaker as you, oh wait, when X is, well, that's weird. Right-hand coil, it ends up, oh, did I graph that backwards? Yeah, I'm not sure what I just graphed on here. Oh, I think I graphed the left coil. Or not. I'm not sure what the heck I did here. Actually, I'm going to delete this graph and see if I can fix this. I want to graph just this thing and this. And insert a graph, or a chart as they call it. And the kind I want to do is just an XY scatter chart. It looks like that. Oh, there we go. Okay, that's better. I was really puzzled by that. And I'm going to change the icon that we've got there because it looks ridiculous with those giant squares there. I'll just use a circular symbol and my dog is snoring here. That's okay. Anyway, that's what it looks like due to the right-hand coil. And when you're at the center of the coil, you get the maximum strength, but it diminishes going to the left. And the same thing would happen if we were moving toward the left-hand coil. But it starts to flatten out, but not until you get to about 0.4, I don't know, about 85% to the center of the coil or something like that. So I didn't want to do that. If I can slide this over here. Okay, there we go. Now, when we look at the two coils together, and I'm sorry, this thing is kind of maybe hard to read. The dots are tiny, but in the center, for quite a ways away from the center to the right, it stays pretty darn flat. You have a fairly uniform field, so it's actually a more uniform field than you get with the other thing. And then as you go toward that right-hand coil, it's dropping off in strength, but it's staying pretty strong here. By the way, this the top graph is actually, the vertical axis is going from 0 up to a value of 1, but we're looking at a much more close-up scale here. We're only going from 1.3 up to 1.44, and I can change that. So I'm gonna, let's see. copy position, size, description. Oh, I don't know how to do this in, I'm not in Microsoft Excel. I'm in the Open Office spreadsheet. But anyway, it stays flat for a while. So that's what the graph is going to look like. And on the left-hand side, remember, we're going from the center to the right. You'd have a mirror image of this going in that direction. So there's a pretty good region right halfway between these things where you've got a uniform magnetic field as you go somewhat to the right or somewhat to the left of the center of the coils. So that was something kind of interesting. Okay, now I want to go back to our other thing and finish off some of the parts of this question here. Okay, so what we did so far was to graph that, and we compared the two graphs. Then, from part A, obtain an expression for the magnitude of the magnetic field at point P. Okay, well, wherever there was our expression that we got. At point P, X is going to be 0. And so we should be able to do that. So at P, X is equal to 0. So I can just set X equal to 0 in here and see what we get. And I'll have B equals, actually, these two things are going to be equal to each other. So I'll have mu naught N I A squared over 2 times, when X is 0 in here, I'll get A squared over 4 plus A squared. That's just going to be 5/4 A squared to the 3 halves. That's the bottom of a fraction there. Then I'll get the exact same thing for this. So I'll have 2 of these, but that just wipes out this 2 that I've got down here. So I'll end up with, let's see, mu naught N I A squared, and we could do various things with this. Let's see, the A squared to the 3 halves can actually, the 1/2 will just give me an A, and then I've got an A cubed in the bottom. So I'll have that, but I'll also still have that 5/4 to the 3 halves. So, and I'm not worried about that so much. But anyway, this ends up leaving me an A on the bottom. So I'll have mu naught Ni over A times 5/4 to the 3 halves. And that'll be the magnetic field strength at the center of the thing. So we could actually do that with the coils that we have at school. So that's actually part C. We got an expression for the magnetic field at point P. But then they ask, calculate dB dx and d squared b dx squared at point P. Well, I'm going to have to come back to this expression to be able to do that. And so let's go ahead and do that. And yeah, trying to fold this here. You can still see that there, and I need another sheet of white blank paper. Oops. Except I do need my expression for B here. And I'm gonna factor stuff out of here. I'm gonna take the mu naught N I A squared over 2, pull that out, and then I'm gonna write it in a different way. I'll have A over 2 plus X quantity squared plus A squared, and write that to the minus 3 halves. And then I've also got something similar. I have a over 2 minus x, quantity squared, plus a squared, also to the minus 3 halves. So when I take the derivatives, I'm not even going to care about this stuff out here. And I just will evaluate what I've got in here. So let's see. Am I doing a dB dx? This is going to be a messy thing. By the way, I'm going to let all this stuff here equal alpha. Okay, it's just constants. And so it'll be multiplying by that stuff. And so I'll have alpha times. When I take the derivative of this, I'll get minus 3 halves times a over 2 plus x quantity squared plus a squared. And then this will be to the minus 5 halves, right? I think. And then I have to multiply it by the derivative of the inside, which is, let's see, going to be 2 times a over 2 plus x, just to the 1. And then the derivative of the inside is just 1. So I'm pretty sure that's what this is supposed to be. If somebody caught a mistake on that derivative, please holler, but I'm pretty sure that's right. And I do get something similar to the other one. I'll have minus 3 halves times a over 2 minus x quantity squared plus a squared to the minus 5 halves. And then the derivative of what's inside ends up being 2 times a over 2 minus x, except the derivative of that one is going to be minus 1 instead of just 1, which will change the sign on that thing. And then that's it. And then I've got the alpha out front. Okay, well, it says to evaluate it at x equals 0 in the center of the thing, or at point P. Well, that's where x is 0. So if I look at this, dB dx at x equals 0, let's see what I'm going to get. I'll get alpha out front. I'll have minus 3 halves times x is 0, so this will be a over 2 squared. Plus a squared. So nothing but a's on that, and that's to the minus 5 halves. And then I'll have x is 0, so I'll have 2 times a over 2, so I'll have 2a here. And that's that. And then I'll have plus 3 halves times a over 2 quantity squared. Snoring dog here. What company is? And that's to the minus 5 halves. Then I'll be multiplying that by just a here. And oh, it's 2 times a over 2, which is just going to be a. So I've got this term and I've got this term, which are identical except for sign. It adds to 0. The slope, or the magnetic field, the first derivative of the strength of the magnetic field at the center of the thing is 0. So that means to either side of the center, there isn't any change in the strength of the magnetic field there. Now, I'm not going to do it, but if you take a second derivative of this thing at point P, you'd probably want to straighten these things up a little bit, but it turns out the second derivative at point P is also equal to 0. And that means you have quite a stable magnetic field in the center of those two coils, at least as long as you're just moving along the axis. And so right in here between those, you've got a pretty stable magnetic field either side of the center. And we were able to see that on the graph as well. Okay, that's kind of enough with the Helmholtz coils. What we're interested in is the fact that they can make an electron beam go in a nice circle. And we'll figure out some way to gather some data on that one of our Tuesday nights. Okay, another problem for today. And this is going to be our last day in whatever chapter we're in, which I think is chapter 28. Yeah, and then starting tomorrow, we're going to be in chapter 29, which has to do with something that happens when you have a changing magnetic field, and that chapter is called electromagnetic induction. And it's kind of interesting. Turns out a changing magnetic field produces an electric field. And that electric field in a conductor can make currents flow. And that's the basis of an induction cooktop, which we happen to have. You have a rapidly changing magnetic field, which your pans sitting on the stove experience. And that changing magnetic field causes electric currents in your pans if you have them that have enough iron in them. And as a result, they heat up. So that's how those things work. Anyway, for this one, different problem. We have a solid conductor with a radius A supported by insulating discs on the axis of a conducting tube. And it's a little hard to see here. I think this was a color diagram in your textbook. So it looks a little better, but there's an inner conductor here. And then in between this inner conductor and an outer conducting shell, there are some insulating discs that keep these two things separated and keep the geometry the same. So, and the central conductor and the tube carry currents I in opposite directions. So in the central conductor, the current is going in this direction. In the outer conductor, it's going in that direction. And the currents, it says, are distributed uniformly over the cross sections of each conductor. So if you picked some spot in here, it would have a current density that's identical to other spots on this inner conductor. And similarly with the outer conductor, they've got different areas, but different cross-sectional areas. But if you add up the current densities over the entire thing, you come to a value I for that. Okay, derive an expression for the magnitude of the magnetic field A at points outside the central solid conductor, but inside the tube. Okay, well, here's how we're going to do that. We're going to use Ampere's law, which says that the integral around a closed path of B dot dl is equal to mu naught times I enclosed. And there has to be a direction to I enclosed. So if we're looking down that central conductor, it's got a magnetic field that is pointing at us, or a current, I mean. And so the current in this case is coming out of the page at us. And this is this little thing here of radius A. But we're interested in the magnetic field that's out here at some radius R, where A is less than R is less than the interior, or the inner radius of that thing is less than B. So that's where we want it. Okay, well, for my Amperian path in this problem, going to be doing it at a radius r, but I'm going to integrate in this direction. And the reason for that is this current is coming out of the page. And when that's the case, it'll make a magnetic field that is circular loops, and they'll be going in the counterclockwise direction. So that'll be my path. Well, from symmetry, I would, and by the way, I can ignore the magnetic fields that are outside of my little Amperian loop because of the symmetry I've got. And so just won't worry about that. Anyway, my integral along this path, B at any point along this path is going to point in that direction. And that's the direction of my DL all the time. So my dot product just becomes BDL because B and DL are everywhere pointing in the same direction along this path. Remember, we're just considering little dinky elements of it. B is constant, that comes outside, so I'll have B times the integral around the circle of DL. It's a circle of radius r. This integral is just the circumference of that circle. And so this will end up equaling B times 2 pi r. And that's just going to equal mu naught. The current that's enclosed by this loop is just I. So it's going to be mu naught I. And B is going to equal mu naught I over 2 pi r. That's the expression for a long straight, the magnetic field of a long straight conductor that we've run across several times. And so we just did it for the center, or the region between the center conductor and the outer conductor of a coaxial cable. So we have that. Part B says to do it for points outside the tube. That is for R greater than C. Well, if I was to do that, I've got that inner conductor that has its I coming at me. I've got the outer shell, or whatever you want to call it, outside the tube, I guess. But in this region here, it's got magnetic field that's going into the page here. And if you consider little chunks of this and add up all those little chunks of current, they'll end up equaling I that we have here. But for that outer part, if you do the integral of B dot dl again, it'll equal mu naught times I coming out of the page and I going into the page. The current enclosed is 0 because you assign a sign to currents if they're depending on what direction they happen to be going. And we've got equal and opposite currents here. So there is nothing here. And that tells us that the magnetic field outside of the coaxial cable is going to be 0. This is a good feature of coaxial cables, that they don't have an exterior magnetic field. Whereas if you have just a conducting wire, it'll produce a magnetic field in the space around it. Sometimes that's a good thing. You can actually, there's a kind of ammeter you can get that you just sort of hook it around a current, and you can measure the current by the strength of the magnetic field it produces. So that's a use of not having a coaxial cable. But if you've got some really high frequency signal that's going through a coaxial cable, you don't want that thing broadcasting all over your house. And so that's why you'd want a coaxial cable in that case. Okay, here's a solenoid problem. We looked at one of these a couple days ago, but this will be another application of the thing. And it's a relatively simple problem. As a new electrical technician, you're designing a large solenoid to produce a uniform 0.150 Tesla magnetic field. That's pretty strong. Roughly, maybe 5 to 10,000 times the strength. Well, more like 5,000 times the strength of the Earth's magnetic field on the surface of the Earth. Anyway, near the center of the solenoid, and you have enough wire for 4,000 circular turns, and the solenoid must be 1.40 meters long and 2.80 centimeters in diameter. What current will you need to produce the necessary field? Well, near the center of a solenoid, the magnetic field, and this is something that's derived in the book and you'll be provided with if we happen to have any solenoid questions on the test, but it's equal to mu naught times n times I, where n is the turns per unit length. Okay, well, we happen to know that this thing will have 4,000 turns, but it's 1.40 meters long. So for this particular solenoid, N is going to equal 4,000 turns over 1.40 meters long, and notice the radius of the thing doesn't even show up on here. By the way, the 4,000 turns, presumably that would be an exact integer number, and so for significant figures, we'll go with the length that they gave us to try to figure that out, and also the magnetic field strength. So we'll just assume we've got that. I'm just going to leave that N alone for now, and I want to solve for the current that would be needed. So the current will be B divided by mu naught N, and the B is 0.150 Tesla divided by 4 pi times 10 to the minus 7th. And I think one of the things in the back may have that in terms of, not helpful. They've got a Weber in there, and I can never remember what a Weber is because it's not a unit that I ever use. So I'll go back to the first section of, I had to do this yesterday, I know. The first section of the chapter. Okay, it's Tesla meters per amp is what it is. So there's mu naught, and then N is 4,000 turns, which is a dimensionless quantity, divided by the 1.40 meters down there on the bottom. And so the Teslas divide out, the meters divide out, and I've got 1 over amps on the bottom, which is going to pop up top as an amp. So this might be a fairly hefty current. I'm not sure. Man, I wish I could sleep at this time of day. Okay, well, not unheard of, but this would be about 41.8 amps. You're going to have You would not want to be using 20 gauge wire for this thing. It would sort of melt it. But if you had a 12 or a 10 gauge wire, you might be able to deal with this. Probably 10, I think. I'd have to look it up and see. But that's how much current you would have to have. All right, this kind of finishes off our part where we're learning about how to make magnetic fields with electric currents and coils and things like that. The Biot-Savart law shows up in here, and Ampere's law. And then our next unit is going to be looking at some effects of changing magnetic fields. And one of the ways you can do that, a fun demonstration I've got a big aluminum pipe, and if I take one of the neodymium or neodymium magnets that I've got sticking to the whiteboard in the front of the room, which last night I got my finger stuck between a pair of them and it pinched my skin pretty good. But anyway, if I take one of those neodymium magnets and try to stick it to the aluminum pipe, it will not stick to an aluminum pipe. And then I take them and I'll drop one of them through the center of that aluminum pipe. Actually, first I'll drop something that's not magnetic through the aluminum pipe, just like a ball bearing or something. Then it falls through it in, a very short time. But when I drop a strong magnet through there, it takes forever to fall through that pipe. So that's one demonstration. And I've got some other ones that I'll show you as well. Things that are not magnetic, still, when you try to move them through a magnetic field, you encounter a very strong resistance to the motion. And it's interesting anyway. So that'll be the topic of the next chapter, and it's magnetic induction. And that'll be the last bit of magnetism that we do. And I think, let's see, I'm going to put up a homework assignment for that, but not have you turn that one in. But it's problems that you will need to practice for that test that's going to be coming up 2 weeks from yesterday. So, or maybe I'll cut it down to a smaller size and say you should also do these other ones for practice, but it'll be less than a full assignment because you've already got one assignment that I think is going to be due next Tuesday, if I remember right. I posted it yesterday. So that should stop us for today, I guess. Are there any questions on the things that we did today? That problem with the Helmholtz coils was kind of interesting, but we took an expression that was already developed, that for the magnetic field on the axis of a current loop, and just applied it to a new situation where we had two current loops and we were looking at the magnetic field between them. So that's things that can be done with some of these expressions. Okay, I think I'll stop recording and